And as I told you, Edson is recording, and we're gonna post the video and the slides. I'm gonna send you an email later to asking for the slides so that we can post them together with the video. So it's your presentation is not showing up here yet. Just
yeah, it's not there because I'm trying to look to the same camera.
Okay. So just a second. So it's a pleasure to welcome Professor Stavale. Professor Fernando Stavale graduated, or he majored in 2002 at Federal Fluminense, and then he got his master's and PhD in metallurgical engineering and materials at UFRJ. In 2005, his master's, and 2009, his PhD. From 2010 to 2013, he did his postdoc at the Fitzhaber Institute in the Max Planck in Berlin. And then right after coming back, he got a position at CBPF. And today he's going to talk to us about manganese oxide surface science studies from bottom to top. So, Professor Stavale, thank you very much for accepting the invitation. It's a pleasure to have you here, and the microphone is yours.
Right. So, thank you very much, George, for the invitation, and also Edson. It's a pleasure for me to have access to your audience because, in principle, I mean, like we are limited on our interaction with people that we are used to work, and then now this invitation comes, and I think it would be nice to show you what we have been doing in CBPF since 2013, and maybe educate some of you that in the audience that might be interested on the topic. So thank you very much once again. And I have the camera here, but I have some of your pictures on the other screen, so I'm going to try to switch to both. So what I'm going to talk today is about the manganese oxide surface science study that we have been performing in CBPF with several collaborators. And I will try actually in my talk also tell you a little bit about what are the other projects that we are engaged in applied surface science and also instrumentation. And then a little bit give you a flavor of what we're trying to do here and try to go to the specifics of this manganese oxide system, why we would like to understand this system. We are, for those that doesn't know our institute, we are the Brazilian Center for Physics Research. Of course, physics research has been performed in the whole country, but in principle, we are the ones in the science and technology environment in the Ministry of Science and Technology that are dedicated to that. And then we are sitting over here, very close to the Botafogo Bay and the Sugarloaf and then Copacabana. So it's quite a challenge for most of the students when they come to CBPF to make their way to the CBPF instead to go to some of these nice beaches here. But most of the time they manage to do it. And over there, we are dedicated to several topics in surface science, but basically we would like to study systems that we can employ, like the model system. It means that there is a physical and chemical problem on the surface, and then we'd like to implement model systems. It means like single crystals or thin films with well-defined characteristics, and employ this kind of techniques that you see here. And then that's what we have basically in our lab. That's basically atomic force microscopy or scanning tunneling microscopy, Raman spectroscopy and surface enhanced Raman. We use a lot of photoelectron spectroscopy. We use pretty much infrared spectroscopy, absorption infrared spectroscopy, and also low energy electron diffraction techniques to try to understand the structure and then find the relationship between structure and reactivity. And then we can divide our current project, or our project in general, in these three like branches here that we look to basic research. Doesn't mean that we don't have an immediate application, but that there we would like to see mainly what are the atomic process that govern that property that we are looking for. And then most of the project are dedicated to the photocatalytic properties of surface. We also dedicate a lot of time in instrumentation. So we had like in the last years projects funded by the HEGI, the Nanospectroscopy, working on UHV setups and also Raman instrumentation, and also microscope instrumentation, so a scanning probe microscope. So that's something that we spend a lot of time. And also we have some projects funded by industry or industry-related problems. So one of them is this surface science of iron ore. So that the Vale company would like to understand how the some certain molecules interact with the surface of iron ores to improve their concentration procedures. And also more recently, some project related to oil interaction with surface. So I'm going to show you some of the examples that I mentioned here. So in the instrumentation, I think it was a nice example that you can find here. Can you see my mouse? No, maybe I have to use a pointer here, right? So let's see.
It's visible.
Ah, it's visible.
Yeah,
so
it's not.
There is a laser here, right? So I can use a laser.
Maybe I am not sure. There should be.
Yeah, I think it would be useful if we try to get this. Yeah, not working so far. Oh. Over here. I need the other screen. Let's say laser pointer.
Okay, there you go. There you go. Okay.
Right. So then in this instrumentation branch, so I have two examples here to show you what we do. So for instance, we are going to see here through the presentation some of these examples. These are zinc oxide films that are very important for their electronic properties, and then we perform characterization about their structure. So then we can propose these structural models based on a lead pattern. Lead is for those that doesn't know, is this low energy electron diffraction, where we bombard the surface with low energy electrons, and then we see the diffraction pattern that originates from these films. And then from this pattern, we can judge which kind of structure we may have. And then we built our own Raman setup to study this kind of films. And some of the examples are here, where we can, from the zinc oxide single crystal, we take like single crystals, well-defined single crystal to see what the spectrum look like. And then we can also perform Raman spectroscopy on a silver, for instance, substrate that's very clean. And then we oxidize this. And then we have from that the film on top, and then we can judge from the patterns that we see or from the peak positions what are the relevant contributions to the band and what's the origin of that. So this is some of kind of example of the instrumentation that we are doing in the lab, so the Raman spectroscope. And then the next example, we also work on a lot of scanning probe microscopes, and then we also dedicate some time to do instrumentation in this branch. So here's an example of a Nanopositioner that we have in the lab. I'm not sure why it's not working. Oh, maybe we have some audio in the background. Can you hear? So, but basically what we are doing here, we are pulsing electrical signal over here to these wires. And what you're seeing here is a plate that is moving because this piezoelectric here. And this piezoelectric are doing actually very small movement, but we're doing thousands of these movements. And then we see this like a millimeter, centimeter range movement, but actually doing very small steps, and then we can just choose one step and then move this plate. But if we do that here in the video, you don't see any movement. So, but this is an example of a Nanopositioner. So it's look like a big device, and it is, but actually it's doing nano steps over here. So we do this kind of things in the instrumentation branch. The other example that I would like to bring here is this applied research. So what we do is the real system, for instance, for the mining industry is actually a mineral that is basically iron oxide and quartz, so silicon oxide. And then when you want to like concentrate this to really like the company want to sell iron oxide and not quartz, not glass, right? Let's say. So it should concentrate itadurites. This is a type of mineral, and then this is made by particulates. So you break this thing, put inside a big bottle or can of water with different pH and molecules, and then you try to concentrate this in a process called flotation process. And then this is a very complicated process, and then the way we try to bring clarity to this in the surface science, we build model systems based on this real problem here, working directly with iron oxide, well-defined surface. And then we use this surface-sensitive spectroscopy or nanoscopy to try to understand how the molecules interact with this iron oxide surface. And then a nice example of that is this 3 iron oxide. This here is hematite F2O3 in different cleavage planes. So this is 1,1 minus 2, 0, 1 minus 1, 0, 0, 0, 0, 0, 1. This is the most common one that we found in the nature, the specular hematite. And then actually what you see in this image are molecules, starch molecules, organic molecules, and then we look with microscopy how this molecule absorb on the surface, how they form, like they build up like 3D structures or more like 2D structures in the other corner here in the left. And then we can even get the insight how these molecules in some cases crystallize in very complex forms that are known in the literature for organic molecules, similar to the DNA molecule, polysaccharide also crystallize in this kind of forms. And then we can, from this image and then a lot of spectroscopy studies, we can build models about how the molecule first atoms and functional groups interact with the iron oxide first surface, for instance. And then, for instance, in this example here that we are working for a couple of years, there is already like some tests in the industry itself or in other with other collaborators in industry, for instance, that they see that with changing the molecule end part, like the functional group, you can see some increase of the recovery of iron. So 5% could be that it doesn't look like that much, but when we look the real problem, that is tons and tons of material, 5% is a lot of improvement. So, and then this final example here that where we can apply the surface science studies is this kind of projects here more recently with Petrobras, where we would like to understand how organic molecules in a water environment, or like in the liquid environment, they interact with not only the mineral, but what are the final atoms that are present on the mineral surface. And then this figure here tries to illustrate a bit of this problem where the ions are sitting with kind of interactions, like if it's electrostatic interaction or complexation interaction, it's very important to decide which process, how you can change the process of concentrate or recover more and more oil from this surface here. So, and then for that we apply a lot of different techniques. Again, we use this methodology with AFM, FTIR, and XPS. And in this case, what is interesting here is look how the molecules absorb on the surface. This is a theoretical work, very interesting, from Caetano Miranda from USP that support a bit of our work. And then here's some experimental data that you see at room temperature and then 60 degrees, how this relatively simple oil interact with the calcite surface. So this is, again, a very well-defined surface with a surface plane. And then we look here how the molecules of oil, these organic molecules interact with oil in different temperatures, different pH conditions, and then try to judge which kind of interaction is going on to correlate with this, for instance, this kind of theoretical models over here. Right. So then let's go for the Mn3O4 and MnO and manganese oxide in general work that we have been doing. So that's actually not a work inspired directly with industry, but inspired with basic science, but it has a lot of implications. So our motivation come actually for this field of research that is kind of an intersection of physics, chemistry, and engineering, where we can call this a kind of artificial photosynthesis. So depending where
Fernando, your microphone went mute. Okay.
Can you hear me now?
Yeah, you're back. Okay.
But we lost too much? No, we're basically. Should I go back some slide here, or it's okay? So now you are moved. I can see. George, I think you are moved now.
Sorry. No, we lost less than 5 seconds.
All right, that's fine. So then let's come really for the subject of this talk. So that is our research topic that's related to basic research. And then actually this is basic because not directly inspired in the industry problem, but it's actually a problem that is an industrial problem itself. So it's a field called artificial photosynthesis, and it's depending on which field that you're coming from. So if you're coming from chemistry, biology, or physics, you're going to like try to tackle this problem in a different way, but you can somehow put everybody in the same basket, let's say. That is this artificial photosynthesis topic. And this means that you would like to create a system that somehow emulate what the plants do, right? And then this schematic here in the left try to illustrate that. So we know that the plants with different photosynthetic centers called PS1 and PS2, they kept this, they harvest the sunlight and then transform this energy in electrons and protons that are able to combine or to process CO2 and HO2 water in the environment. And then what they does is actually like a series of very complex chemical reaction result on glucose, right? In glucose, so a sugar, they can grow up, they can grow a fruit, and then they're also in this process, depending on the cycle, you have like some production of oxygen. So from the physics perspective, some would call artificial photosynthesis when you try to emulate with a material system. This is a picture here that you can find in literature of titanium oxide nanoparticles. You try to emulate some parts of the whole reaction, that's very challenging, or you try to emulate a part of this reaction. So one of them is split water. So there's other people that also look for the CO2 oxidation to form really like complex carbohydrate molecules. But one way to look this is, in a simple way, would be like, can I find a material that absorbs sunlight in a preferable way, to split water and then form stoichiometric amounts of hydrogen and oxygen. And then in this branch, there is a lot of systems like the zinc oxide that they show here, and many others that try to emulate this situation, harvesting the energy that comes from the sun. And then to do that, usually you have to deal with the material band gap and then the reactivity of the material. And then you can do that doping this material or decorate this with metal nanoparticles. So that's the way to look this. And then that would be one way to look in the atomic scale what the water splitting reaction how can it be performed in different materials. And you can find here work that we published a few years ago, some of this summary, some of this challenge. And then usually the challenge is find the material that can absorb light, and then you find the material, but it's not good enough. Then you change the doping level, and then you change the doping level to create more electrons and holes that actually are the combining centers for the water splitting, and then for the hydrogen recombination. And then usually you have to change the size of this material, change the dopant, and then most of the time change the kind of co-catalyst that you put on the surface, like metal nanoparticles or metal oxide nanoparticles, to bring this reaction as an effective way. And then something that inspired us here is this manganese oxide. Manganese actually is a very important cation that is present in these enzymes in the plants. And actually there is a lot of works in the literature that bring attention for this complex, that actually very complex, because the structure that they form is difficult to emulate by physical means. That is based on manganese, calcium, oxygen. So it's really like a special form of a cubane that is a distorted position of the manganese. But the general idea is the manganese ability to change the oxidation stage and change its structural properties is the one that is governing this photocatalytic activity of many enzymes. And then inspired on this problem, we decided, like as let's say as a physics person would like to deal with the problem, is like let's reduce this problem to just like a small piece of this. So, and then a small piece is, let's grow manganese oxide and dope this manganese oxide with different methods and see how we can emulate and understand this process from the fundamentals. And then why then this manganese oxide is important, as I wrote here, because it's different oxidation states and different structures that can assume. And then this affected dramatically the electronic properties of this. So that's why our main goal and the following results that I'm going to present to you is investigate the structural properties of these oxides, how we can change this oxide with dopants, and then at the end, of course, study its reactivity. Right. George, I think I'm already 20 minutes, right? I'm half away.
Yeah, as I told you, you can go 45, 50 minutes. Leaving 5-10 minutes for questions.
Right, great. So then let's go for the manganese oxide itself. So here I have an example of what we have been doing, right? So we have here manganese oxide is MnO, that's relatively inert, because the oxidation state of the manganese here is only +2. But we have grown these films on top of gold substrates. And then this is some of the results that I can present to you. So this is the typical lead pattern that we obtain, where when we analyze the position of these diffraction spots and the distance between them with respect to the substrate, the underneath substrate, that you can see basically here, very swallow, we can judge what's the position of this oxide on top of gold, and then judge about the structure of this oxide. To add to this kind of characterization, usually we perform Scm imaging. So it means that we use the scanning twin microscope, where everything that is bright here is where you have more electrons. Usually we can assign this to the position of the atoms. And then we can recognize some of the structure that we identified here in the diffraction pattern. That is this square pattern over here. Here you also see a part of the substrate that is not covered, and then this is useful for us for judge the height of the structure that we are seeing. So because we have directly a step edge here of the gold 111, and then we can judge as an internal calibration the height of these islands here. What is interesting is we can change the properties of this film, change the deposition procedure, and also the amount of material that we deposit, and then obtain relatively thick films that serves us as a model. So you see here some image of transmission electron microscopy that is done by the group of Braulio and Chet there in the E method of one of our films, and then we can judge here with these cross sections over here exactly the structure that we expect for the manganese oxide, the MnO. And then from this position here, we are pretty sure that we have a very, let's say, well-defined MnO. And then based on these properties here, the amount of defects that we have, the amount of the terrace atoms, we can perform this kind of characterization that you see here with X-ray photoelectron spectroscopy. And then from this peak analysis that you see here, that's pretty extensive, but we can judge how much of the type of defects we have in these oxide films. Because we know from these peak ratios here, the amount of manganese with low coordinated sites. So this is the work that Chad has been performing and analyzing. And then this is very useful because for now we have a very nice model for the MnO film. At the same time that we can also with the spectroscopy signature judge how much we have of low coordinated sites of manganese in this oxide. So it is a nice way to not only prepare a nice system to be investigated in future adsorption reactivity studies, but we also add on the interpretation of these lines here. And these lines, I'm assuming that most of you now are not like specialists in XPS. I already introduced you a little bit about SCM, about the protrusions, but I think it would be useful for you to understand a little bit of this spectroscopy. So here's an example of the machine that we have there in our lab in CBPF. And XPS is based on the extraction, or let's say that we take off electrons that were previously bound to very specific electronic state in an atom. And to do that, we inject photons with high energy, so X-ray range of energy. So here's aluminum. And then the electron is ejected. And then if you do that, and then this electron is analyzed with electron analyzer, like this one here, we can say which energy it has from the orange, because we know what's the photon energy in the beginning. So it's just a photoelectric effect from Einstein. And then from that, we can say what's the bind energy of this electron, where it was sitting before. And then from the shape of this peak, all the component that you see inside, and then here's an example here in the right corner, we can judge which kind of oxidation state this atom has, and then which kind of species is binding. So it's just oxygen, or it's a hydroxyl group. So this is very powerful information to tell you not only which element you have there, but what's the chemical state of this element. And this technique is pretty much limited to the surface of the material, because different than the conventional one, let's say, energy dispersive spectroscopy, as you see in like electron microscope image, where you excite a large volume, and then your signal is based on the X-ray, the characteristic X-ray photons emitted by your atoms. Here in the XPS, you actually get just electrons that are scattered. And this electron can only conserve energy if they come from this region here, the surface region, between 1 and 10 nanometers. So this gives us a lot of a powerful tool to understand what's going on the surface, and then where the chemical reactions go on. That's why that result on the MnO is very important for us to judge how much things that we cannot see from an image like that, but how much terrace atoms we have, how much defect atoms and kink atoms we have on the surface compared to the bulk atoms, because these atoms are the most reactive in any material, of course, because they are low coordinated atoms. So on this idea, we have also explored the properties of MnO3O4, and then this is just add up with that idea that we would like to understand the chemical reactivity of the manganese, also what's happened there in natural system. And then here, just like we can employ the same like methodology that you saw before, the MnO, now we have MnO3O4. And then we can look for the diffraction pattern and judge the structure of this film. We can look with the Scm image where these atoms might be sitting. And we can also judge from the transmission electron microscope cross-section image which kind of structures we have, and combine all these three here to have like a very robust model about this system. And then again, look for the peak positions and then see how. I think it's a nice example. All you see here is a tick dependence and temperature dependence. You see MnO3O4 in the same plane of growth direction, but you see that the peak shape change for each one slightly, and then these changes are telling us the small changes that we have actually in the amount of low coordinated sites in this kind of film. So this is very helpful, and then this is also something that we can correlate with higher resolution image. For those of you that are not familiar with nanotransmission atom microscopy, what we're doing here, we prepare a film, we cut this with a focusing ion beam microscope. Actually, Brown and his group do that there in metal. And then you can like cut this film and then look to the side of the film. So then we have both information. We have the top surface information with our microscope combined with this cross section that add up to find actually the structural termination of this film in both ends, on the surface end and also in the interface end with the substrate. And why this is important, because when we try to understand the properties of any of these kind of films, you have to take into account how it change or exchange electrons from the atoms in the interior of the film with substrate, where you have a metal that is a reservoir of electrons, and then how it's going to affect the stabilization of the topmost surface, because there is where the reactivity go on. So here in this model, I think it's useful to explain a little bit more details what we're seeing here. So these red atoms that you see here are actually manganese Mn3O4, but this manganese Mn3O4 has a spinel structure where manganese plus 2 is sitting in a tetrahedral environment and manganese plus 3 is sitting in an octahedral environment. And then that's why the green here is sitting in this side, that is an octahedral side, and this here is a tetrahedral side. And the reactivity of any of these kind of compounds, and then you can also include hematite, F2O3, that is a spinel structure, or cobalt-3 oxygen 4, that's a very prominent oxide. All of them, the properties, the chemical properties of this system depend dramatically on how the surface terminates. Because if you have here atom that is like a +2 manganese, it's sitting in an octahedral side, and the way it shares electrons, the amount of charge that you expect in this atom here is different than this one, because it has, because the chemical bond and the possibility of tetrahedral distortions or octahedral distortion, this change the chemical environment and then promote the chemical reaction of this material. So it's strongly dependent on how the surface is terminated. Right, and one way to modulate that, so change this props, I'm going to show you, I think in some of the last slides in the next 5 minutes. Right, so the last type of oxide here that we have been investigated is the Ma02 film. So this is a very challenging film that we just touched recently with the work of Shadi. So you can transform some of these oxide films to MnO2, and MnO2 is very challenging because it can assume a lot of different polymorphs. So then it's hard to obtain this film in a very defined way on surface. But we had some examples here that we succeed to do that. This is, for instance, the lead pattern for the Mn3O4, and then this is the example that you can see. This is quite different energy here, but still, like it's a good example that shows the structure, the spot structure that you see is pretty different than the one that you see for the Mn3O4. And then we can judge if this is really the oxide that we expect from the structure of the peak, the XPS peak. And then this is quite important result to be developed in the next years, because it's the one that's expected to have the highest reactivity or more preeminent to be reactivity, because it's not manganese in +2, manganese +2 and 3, but it's manganese in +4 oxidation state. And then it's a very unstable situation where it is easy to the manganese to be low coordinated and then later exchange electrons with any molecule that is found on the surface. So we have been employing this kind of methodology. I'm going to go into my conclusions here, showing the next example. But we have been working on this system in different substrates. This is a very important thing because it helps us to understand when we grow a film in a substrate and then use another analog, like the copper substrate, we learn that we can stabilize different phases. So this is MnO, but in a different phase that we stabilize in gold. And then this is important because on copper, you have a lot of catalytic properties that can bring to the system the combination of manganese oxide and copper oxide. And at the same time, we have actually a nanomaterial that has very unique properties, although it's the MnO, but because it's a MnO001 with this 1/2 superstructure on the surface, we have a lot of low coordinated atoms that are expected to play a role on the reactivity, especially for the CO2 oxidation, for CO oxidation. Let me jump here a little bit. This just bring you the last example. That's what we can do with this reactivity studies. So then let's go back here to the Mn3O4 and two situations that we are already looking to to this model system for the reactivity. So you're seeing here again Scm image on one of those Scm images that you saw before, but now we are absorbing water on top. So again, Scm is based on the tunneling process, and then you are actually collected more or less electrons in certain position of the surface. But because we know that the atoms are surrounded by a large density of electrons, what you see in the Scm is actually the amount of electrons that you have in a certain position. And then because it's usually localized in certain positions close to the atom core, then you can say, oh, that's my atom there, right? So you're not seeing the atom, but you're seeing the electron cloud. But then usually you can directly address more electrons where the position of the atom is. Here are some examples where you see bright protrusions, that the way we can say, or dark areas. Everything that's bright is higher. Everything that's dark is down. It's like a morphology image, but it has this interpretation about the electronic structure. And then here in this image, we are following with different water exposure in the work of Huben. And the Scm image, we can assign and find from these indicators here where this amount of this water molecule are sitting. So then we can try to find a model which position of this line the water molecule sits. If it's on top of the line or in between lines, and then we know the structures of this line. And then we can follow as with those different amount of water and different amount of or change temperature, what's happened with these structures here. So if we have, this is a nice way to see. You see here in these two blue circles, bright protrusion that over here become dark protrusions. So from these changes on the image, we start to assume what kind of reactions forming or happening. And then we can say if we have in the beginning some kind of what appears to be a molecular absorption, and then later on, as you dose more water, or you change the temperature, or you just let the kinetic go on, so time goes past by, then you see that the water can dissociate from different protrusion, and then finally it can leave the surface, and then we can try to think about which kind of species were on the surface, and then how this affects the reactivity of this surface. As a final example here of this series of studies that I tried to make a compilation here that about the bottom to top. Now the bottom is we are looking since the interface up to the top of the oxide. I bring you this example here. That's the Mn3O4 also films gone in the thesis of Astrid, where we try to change the properties of this oxide, doping this oxide with small amount of cobalt. So we did a lot of Mn3O4 on gold and copper. The best way to do this doping is on gold, actually, because we can find the spectral signatures better on gold than copper because some overlap of this peaking, the peak positions. But at the end of the day, this result here is Mn3O4 doped on deposit on gold. These are some of the schematic, how we prepare this film, how Astrid prepared this film. So we grow the Mn3O4, and then make a lot of intercalations of the deposition and annealing procedures to end up with some preparation that indicate that we are doping the system. So these are the manganese 2 core level peak. Here's the cobalt 2 core level peak. And actually, you have here the two peaks, the two envelopes correspond to the non-doped and the doped one. We almost don't see any change in the doping one. We also don't see most of this change of the doped one in the lead pattern, so they are pretty much the same. Maybe here this is just a matter of a different contrast, but the structural properties appear pretty much the same. But we see in this doped one the peak that correspond to the cobalt-2 peak. And then this cobalt-2 peak can also be recognized when we look to the spectra, so the photon emission spectra of these films, non-doped and doped close to the valence band. And then there in the valence band, here's the Feynman position. We see a bump here that we can assign for the cobalt-3D. What's nice about this is when you're doping something, you don't want to do like a mixed oxide. You don't want to prepare like let's say quaternary oxide. So you want to have a small amount of a dopant that change the electronic properties, preserving some of the structural properties of your host material. That's the MnO and then when we see that this is structurally pretty much the same, and then we just see a difference because the electronic contribution that appear because the cobalt, we have a lot of evidence that we are actually doping and not forming another type of oxide. And then we can add on this on many other analyses about the vacations formation. We perform a lot of experiments in the synchrotron as well, using X-ray absorption spectroscopy, where we can see signatures when you take this kind of absorption spectra, X-ray absorption spectra, in different angles that reveal more like the bulk and the surface contribution. And then when we compare this with what we know from the literature for cobalt oxides that we would like to avoid, and then to some examples of cobalt doping zinc oxide materials, we find a lot of correlation. You see here from this three-peak structure here to the cobalt sitting in a tetrahedroside. So from that, we can build this kind of model that we see here, similar to the other one that I showed you before, where we have the the manganese +3 in the octahedroside and the manganese +2 in the tetrahedroside. We can judge with this combined experiment that the cobalt might be sitting actually in the tetrahedroside. And this is important because the chemical properties of this system will depend on that. And also that we expect that some of this cobalt is actually sitting, of course, in the center of the film, but most of them in this low coordinated sites on the surface, with something that would promote the chemical reactivity related with the doping of the film. So with that, I hope that I have shown you some of these examples that we are working on from bottom to top of the atomic level investigation of the physical and also chemical characterization of manganese oxide surface. And then we could address some of these properties that are very relevant to build a model system that we can determine the surface orientation and in some cases also the termination, that are something different. We saw from the spectroscopy some electronic properties dependence on these growth conditions, so this would affect the chemical reactivity. We could see that we can implement some doping strategies and procedures to dope these films in a controlled way. And chemical reactivity is something that is ongoing investigation, but I have already shown you one of these examples, that's the water absorption on one of these oxides. And then we expect to go through this kind of studies in the next months, years, if we don't have another pandemic and is not delaying this kind of goal. So with that, I would like to thank your attention, and I'm very happy to answer your questions.
Thank you very much, Fernando, for the very nice talk. Many results, interesting results. So we are open for questions. I see Werneck has already turned on his microphone, so probably has a question. And I see that we have our DFT people are in the audience, so they probably will ask questions too.
Oh, there are some DFT people now. That's not nice. I showed too many models without the DFT calculation. So
yeah, but that is a
controversy.
It's kind of a cue for them to ask questions. So, Edson, do you have any questions? So if Edson doesn't have, I think one question that I was going to ask, I believe you answered. I was going to ask if use of nanoparticles in some of your experiments is just to increase the surface, or when you use nanoparticles, you are also changing the electronic structure of the system, depending on how small are the nanoparticles.
Yeah, we did already a lot of studies on silver, gold nanoparticles deposited on oxide surface, where we would like to see what are the facets, what's the size that is stabilized on that surface. This kind of example I did not brought here to you guys right now. You still can see my screen?
Yeah.
Mm-hmm. Yeah, right. So all these examples that I have shown you here are just flat surface with different oxides preparation and orientation. The nanoparticle I mentioned here is like this one here, that we know that all the surfaces that we saw here, they can be modified with the decoration of nanoparticles. But was not the subject of this manganese oxide so far.
Sure.
Right. So, but one thing that is still missing, for instance, in the study that I have shown you about the cobalt doping, is there is a chance that some amount of the doping that I expected is doping the oxide could be segregated to the surface. And then to settle this debate, I need to do the Scm image of the doped system, something that I have not shown you because we have not done so far. But from the spectroscopy measurements, I don't see any evidence that I would have like a cobalt metal nanoparticle, but because it would have a very clear signature in the spectroscope point of view. When we would like to modify the oxide with doping, then I can show you, for instance, this kind of examples here that I worked before, and we still publish things on this direction where we really like have a flat surface. Here's MgO, not manganese, magnesium. And then you can decorate with gold particles or silver particles and see how the particles evolve and how they change the electronic structure. But that was not subject of the manganese oxide so far.
So the nanoparticles do indeed have a different, they are small enough that they have an electronic structure that is quite different from the bulk or a thin film or something like that, right?
Yeah, so these nanoparticles usually, this is not nanoparticle. For instance, this example here, so then we are talking about nanoparticles in general, right? So for instance, this example here, we have gold nanoparticles, and then from their shape and size, I can judge actually what the facet that they're exposing. Some of these particles here in this example that we are like depositing gold nanoparticles on bare MgO, and then on doped MgO, they can change their growth behavior and form this kind of 2D growth. That's why they look like different here than this one. And then these are particles that have a pretty different electronic properties because they are, in general, when they are 2D in this oxide, they are supposed to be charged. So they have an electric imbalance. So they are like charging. So they have some kind of Coulomb blockage that can happen because they're small, and then they are on a non-conductive substrate, and then something of subject in many different for different studies, and then they are expected, even that they are not like let's say 2-3 atoms big, but they are for sure different than a big nanoparticle because they don't have means to exchange electrons because they sit on top of oxide. And then this is basically the reason of the reactivity of a lot of metal nanoparticles, because they start to charge up like positively, they have excess of electrons or less electrons that they should have. And then this is something that brings reactivity. So when the molecules interact, they are going to change, they are going to be prone to react with these particles. Okay. So yeah, if maybe I'm not answering your question, but what we expect is that.
No, but I understood. It's basically the size. So the size can be such that it will have an extremely different electronic structure. We will act like a quantum dot in some cases. Like you said that you have two blockades, for example.
I mean, they are different because I think this is example here. It's nice. This is work with Pacchioni from Inter. For instance, what's happening is, of course, these particles are sitting somewhere. So they are sitting on top of oxide. So if you look for the orbitals that are being like contributing to, well, let's say for the overall material, they are sitting somewhere in the band gap of this material. So they are not part of the material, but they are sitting somewhere. And then they have this, let's say this, they are sitting in a Fermi energy, they're sitting in a electron reservoir, that's the oxide. And the way they're gonna like exchange or align the states, like the oxygen 6 acid states, to the oxide itself states, make like actually electrons being promoted to one side back and forth. But they are not, usually they are not prone to become like a quantum dot, because in the quantum dot you have a so dramatic change in the electronic structure of the particle that the properties are related to the particle itself. And then here is the conjugation of the particle on that oxide. Okay. So if you change the oxide or the dopant, you are going to see, of course, that the conduction band or the valence band, they are actually more or less aligned to these metal states. And then this promote, of course, different occupation of the orbitals. But it's not really like, it's populating state that maybe were not populated, but it's not really changing completely the states of the particle itself, like in a quantum dot.
Okay, okay. I see that there are no written questions, but I have a few more questions. I noticed that the majority of the spectroscopy that you did in manganese, you are exciting electrons from the 2p shell, from the 2p orbital. So why is that? Why there is this preference for the 2p excitation?
Right. So in general, when you look for XPS spectra, you are going to try to look to the electrons that are more like sensitive to the chemical environment, right, to change. And then for this reason, you would like, for instance, to see like a theoretic, what you would like to see. So we would like to look to the 3D electrons, right? So let me see.
Yeah. Yeah, I thought you would excite 3D electrons.
Yeah. So, the problem is when you look to the 3D electrons that are actually hybridizing with the oxygen 2p, they are delocalized, right? So we expect that they are not like so localized as the 2p. And then, by a matter of fact, all these states are very close to the Fermi energy, right? Okay. So it's implied that first you see here manganese 3D states, and it is spread to a large range of energy. So it's very spread. And then over there, you have all the overlaps that you expect in the band structure, right? So you have the hybridization with the oxygen 2p, you have oxygen 2s. So all this together makes it very difficult, the analysis here of the 3D orbitals of any transition method. Okay. So, and then what you have next as a choice when you use XPS. So the ideal choice, and we have been doing that, I'm not showing you here, maybe in the few slides up. Let's see. So for instance, this is an example here. So you want to look at, and then while you do that, you can go to the synchrotron, change the energy of the photons that you're using, and then try to excite in a resonant way what's happening in the valence band. So first of all, you cannot excite just the energy that you would like to see, because you're going to see everything that's happened after. So you can excite some like 2D levels or another level. So you can change the energy over here. This is different film thickness. And then even if you're in the synchrotron, super high resolution, look how your valence band, top of your valence band look like. It's pretty broad, you see. So all the states you see here is still like 3D, oxygen 2p, and the mixed states. But even if you are in the synchrotron, high resolution energy, and electron analyzer, you see that everything is pretty broad. And then it's difficult to judge which kind of oxides you have and then which kind of environment. So the technique of choice, you usually then look to the 2p electrons. So let's get an example here, the 2p electrons. So these 2p electrons are affected by by an environment because the occupation of these electrons, and then when you excite them, they are promoted in two ways. One is ejected directly, the other one goes to the empty states of the 3d electrons that are on the bottom of the conduction band, right?
Okay.
So they are very dependent on the chemical environment, because when you excite them, you have to promote them to somewhere, and then they don't go anywhere. And then when you excite them, they later on, after this hole is created, they have to be de-excited. Electrons promoted there. So at the end, they're very sensitive to the chemical environment as well. And then the one way you can see most of the transition metal oxide is you look to your peak position, your main peak position. You look to the distance of this main peak position to satellite structures like this here. Satellites, because they are actually orbiting, they are close to the main peak. This is the 3.5, this 1.5, this pin orbit splitting. And then depending on the shape, look at the shape of the Mn3O4, compare it to MnO. So you see that there is a satellite structure here. The distance of the satellites is different to the other one. So the shape changes here. So you get a lot of information there. That's why you look to the 2p peaks. And of course, I mean, like the way that the XPS experimental technique was developed is you use generally aluminum or magnesium sources, so K-alpha sources. When you choose one of them and then look to a very large amount of materials, so basically all materials in the periodic table, you're going to realize that the cross section, so the intensity of these peaks of the 2p are much intenser than the other ones. So the reason for that is the orbital shape, the energy that you use, and all that. So at the end of the day, the 2p are the orbitals of choice because all these reasons, right?
Okay, okay. So my initial guess was the cross-section, that the cross-section was larger, but it's more than that. You get more accuracy and you get more information too.
For the conventional aluminum source in all labs around the world, you have more cross-section, as you say. But when I show you that example, that we were in the synchrotron, and then you try to excite with different energies, so you change actually in the cross-section, right, sensitivity, and it's still like a mess, right, because the peaks are still very broad, and then very hard to see tiny change. So it's all this together that brings us to the 2p from, I would say, all transition methods. That are the peaks that we should analyze. Okay,
okay. The other question I have is exactly for this kind of simulation that you, it's not showing anymore.
No, I can go back.
Okay. This slide. You have this simulation, these many colorful Lorentzians, I would say. Is that a package that comes with the? I know that these instruments are very expensive, and they come with a bunch of software packages that do the interpretation of the results, or is that the work of some colleague, theoretician, or collaborator who is doing the interpretation?
First of all, the structural models or the peak deconvolution?
The peak deconvolution.
Right, so then it's not actually a simulation, then it's a fitting process, right?
It's a fitting, okay.
It's a fitting. And then actually what we do is we profit from the literature, of course, that, I mean, we do the fitting, so Jade, Astrid, all my students do that. The packages are not coming with the system, so you have to pay for it, but then it comes. And one of the very well-known package is the CASA XPS that we use because it came with our package that we order. There are other in the literature, people use a lot of Igor Pro because then you can use the true voids functions. But in the CASA XPS, that's a common package over, and XPS peak fitting is another software that you can find that is free, like Igor. And then you use like some routines to decide, for instance, we have a meeting a manuscript exactly discussing about that, but So let's see this example here. So this, can you see here?
Yeah,
More details, right? So what you have to do here is you need some guesses, right? So you know, for instance, this is one type of peak deconvolution. We use that not that often, but we can say like an empirical model based on actually the multiplet splitting. So actually how the electrons are created, extracted, and how many holes you have in the 2p level. So you have 6, let's say, boxes, right? So 3 for the 2p 3.5, 2 for the 2p and a half. This box is what I'm saying is, right? So you get the 3D, to get the 2p orbitals, you know how many electrons should be there. So, but then you have like an oxide, so it's not a metal. So you have like a spin orbit splitting, right? Because you have the interaction with the crystal field of the oxide.
Okay.
So then now you have the levels, and then you have to occupy this. That's why you have one that have 3 boxes that you can put in each one, like 2 electrons, right? For from the electron occupation rule, right? So then you have more intensity in one and the other one. And then you know that this ratio should be respected. So 1, in this case here, is half of the other one. So now you also know that, for instance, for the 2p, you know that the one state of this, let's say when you create this hole in the atom, so you don't have like a neutralized atoms, you know that you have, it's in an ionic state. And then you know that for the selections, you can count how many transitions you should have. And you have this Mn manganese in this octahedral environment, you expect that you have like 4 ionic states. So then you make a guess that you should have these peaks in a certain position. And the ratio of these peaks should also respect this ionic state probability. So one person that is well known in the theoretical field that work on this system that we collaborate as well is Paul Bargus. And then we can profit from this publication that we have in the literature as well. And then we can say, so manganese +2 in the octahedral side should have 4 peaks. But then when you look to the system, we need to include one more peak because we don't understand perfectly the satellite structure. So then that's the empirical one. So that's why we are going to like adding, let's say, stuff for your fitting to make a full interpretation. So based on the theory and based on the empirical data that we have. And then for that, we know also for this ionic state, for the manganese 2 plus, what's the distance should be for each level or approximately each level. Then that's why you start to make like some constraints. So what's the position of these peaks should be more or less this position. The width of this cannot be smaller than our resolution, cannot be larger than a reasonable one for the physical meaning. And then in this way, we're going to like with the fitting procedure. So the way you choose the background strongly affect the peak full width, half maximum. So all these things should be taken into account, but we are actually using theory and let's say physical and empirical reasoning to decide how should be these peaks inside and then judge which kind of oxidation state we have and what is happening when we're changing the film thickness or structure, right? So usually we don't, so far we're not collaborate that much on people that simulate XPS spectrum because actually something that even people in the DFT community, and then maybe some of them can criticize that, they don't like that much to calculate the spectra itself, because there is a lot of fine effects, right? So, and that is not easy to account for Frank Compton vibration and so on. But we are also open to this maybe in the future. Okay.
So any other questions? Anyone? We still have Edson is still there.
I just
yeah, Edson, go ahead. Your camera is off, it seems.
My camera?
Edson's. No, Edson's camera. No, your was fine. Yeah.
Okay.
There you are.
I'm so sorry. I missed great part of your talk because I had some problem with my internet connection. So, but anyway, I and substrate.
Right. So I'm very happy to take part of this meeting, and I hope so. If people maybe are shy or are not aware about some of the techniques here, just write me an email and then remind me that it was here, and then maybe maybe no, I'm going to reply you, and then we can clarify some of the points here. Also about the techniques. So it's also good to promote this combination of experiments, because they bring us a lot of confidence to propose some of these models and this interpretation. So that's also something that we spend a lot of time combining all this methodology together to be more assertive, to be more sure about the experimental results, and then I hope to also promote this approach for those that I would like to apply those in their problems as well.
I was making these questions in a little bit of detail because we are, Edson and I, we work with the strongly correlated systems. So we are at a level where the models are really like toy models. They are really far from reality, let's say. You don't get details, but DFT cannot, let me see, the DFT people are gone, so I can say that. The DFT has difficulties to include correlations, and it's unable to include the strong correlations. With the strong correlations, everything breaks down. So you have to go quite to much simpler models. You strip most of the orbitals, you just get the orbitals that are close to the Fermi energy, make a very, very simple Hamiltonian that you can write with a few terms, and then you add correlations somehow using some technique. So we are very far from being able to get in the details that the experimentalists measure, but I just had contact with some papers where you can complicate a little bit the toy models and then get at least a qualitative comparison with the experiments of, I don't really know all these spectroscopic techniques, Shannes, leads, and everything. For me, it's a soup of letters. I never know exactly which one is which and what they really do. But I know that you get excitation from one level to another, or you get photo emission, or this kind of thing, at least the basic idea. So I got interested on that, on the possibility of cooking up a little bit more complicated model that can at least qualitatively be compared to what experiments.
Yeah, so just adding then for your comments, so although here we are doing like this model system, I think the result that you have for your...
I came in contact with that in the last... Yeah, go ahead.
Just to maybe a comment about what you said is that makes sense what we are doing here. I mean, like one thing is, although your toy models for us here from an experimental point of view, these are also toy models. Let's say the surface that you see all around in the real world not necessarily share the same properties here. So we are really like in the ideal environment most of the time. We try to make the correlation with the applications. That's what we try to bring as well. But it's very often I see people that are looking for transport properties of these well-defined nanostructure, nanowires, and so on, is using, for instance, this approach here. So you prepare a well-defined system in vacuum, but then you need a technique that is able to probe this. And then come the SCM, that's some of the examples that I show you here. The problem is, or ARPS, because we also do that with Wendell in the synchrotron. Now I'm just putting here in the side one of our measurements and then some different calculations for the top of the valence band and the bottom of the conduction band that we did with cisternas there in Chile. And and this is actually already published, it's not here. You can explore with ARPAs and SCM some of these properties. ARPAs, the difficulty is you need a periodic array, you need a lot of them, and then they should promote like a formation of a band to assess this information. But the way to assess this information is to prepare this kind of system that I show you here. The other ones is you have just one unit on the surface. So the way you have to do is prepare this unit, this wire, whatever, and then you have to go there with your SCM tip and perform what we call scanning tuning spectroscopy. Most of the time when people in your field are successful on that is when they look for the signatures that appear in the dense of state close to the Fermi energy. If a band gap appears or you have a localized state, the problem is to see this kind of effect where ballistic or a specific type of transport appears, you have to get out with the KBT, right? So the thermal broadening, you have to put out a lot of things, and then at the end of the day, you have to go back to low temperature SCM. Okay. So that is something that would be very useful for you guys. Unfortunately, we don't have. So as I said, we got this project with Kyle, but so far we didn't get the resources to purchase the system. But the idea is if you have a SCM at low temperature, you have a chance to place your tip there and then see this quantum effect, this quantization, or this phenomena that is governed by the to quantum particles, so the quasi-particles. Otherwise, everything is mirrored out, and then it's not accessible. Although you have the right sample, but you need to go down in temperature.
Okay. Like you mentioned about the Majorana project that you were have with Múcio and Caio, right?
Yeah.
Okay. Okay, very nice. Thank you so much. We are gonna be emailing you shortly to ask for the slides so we can post together with the video. And I send you the link of our YouTube channel too, so that if you want to advertise to your colleagues that your seminar, it should be posted probably next week because we have to download it tomorrow, and then next week it should be posted.
Okay.
So
thank you very much.
Thank you very much for accepting the invitation, and say hi to Múcio in case you see him.
I will.
Yes.
In case I see him, yeah, that's true.
Yeah, I know that he's not going there. Maybe next year. Who knows? Yeah.
Next year for sure.
Yeah. Okay.
All right.
So nice, very nice meeting you.
Thank you. Bye bye.
Bye.